Okay, so for this session, I'm going to be talking about alcohols mostly and related functional groups like phenols and ethers, thiols, and sulfides. Alcohols are your OH group, but more importantly, the OH group is attached to an sp3 carbon because if it's, let's say, attached to an aromatic ring, then it's a phenol. If it's attached to an sp2 hybridized carbon, then it's an enol. Okay. Just like with alkyl halides, we can classify our alcohols being either methanol or methylic, a primary alcohol, secondary alcohol, or tertiary alcohol, depending on how many carbons are attached to the carbon with the alcohol group. Okay, so primary alcohol, the OH has a carbon, and that carbon has only one carbon attached to it. So primary alcohols are also known as terminal alcohols. You'd have your secondary alcohols, so one carbon, one carbon, one carbon, one carbon, okay. Tertiary alcohols, three, etc. Okay. So alcohols are a very important functional group in nature and in our bodies. Ethanol gets you drunk, adrenaline gets you pumped up, cholesterol supports your cells and metabolism, glycerol, the back chain of all the fats in our body. Okay, some properties of alcohols. Alcohols can be somewhat acidic or acidic enough if you treat it with a strong base. And if you treat it with a strong base, it becomes an alkoxide or the negatively charged oxygen. So it's like a deprotonated alcohol is called an alkoxide. So there. So, okay. And then since alcohols don't have any resonance, their acidity depends on the inductive effects. So like this example, if you have a lot of fluorine groups near the OH, then it becomes very acidic or very small pKa. So you've learned this already before. Because alcohols have OH groups, they also have H bonding with each other. That's why they tend to have higher boiling points and they tend to be soluble in water. Okay. Now, compared to your halogens or your alkenes, alcohols actually take higher precedent or rather higher priority or take precedence in naming. So now, not only do you want to find the longest possible parent chain, but now you also have to find the longest possible parent chain that includes the alcohol. And when you number your alcohol, you have to try to make the alcohol at the lowest possible number, not anymore the first branch, but now the alcohol group. So in this one, 2, 3, 4, 5, 6, 7 chain with an OH. We number from the end near the alcohol. So this is 3-heptanol or heptan-3-ol. Okay, so that would be then, okay. This one would be 1, 2, 3, 4, 5, 6 or 1, 2, 3, 4, 5, 6, 7. So heptane, but since it has a double bond, it becomes heptene. And then because it has an alcohol, hept-10-ol. Okay? And again, alcohols take precedence or take priority over other functional groups like alkenes. So now numbering starts here near the alcohol. So it becomes a 1, 2, 3, 4, 5 methyl. And then 6 hepten to all. Or it could actually be 5 methyl hept 6N to all. Okay, I'm not gonna be very strict with that. Okay. Cyclic system, alcohol's first priority. 3,3-dimethyl cyclohexanol. This one, alcohol's first priority. Second priority will now be, instead of your branch, will be your next functional group, which is alkene. So this is another enol, okay? This is 1, 2, 3, 4, 5. 5,5-dimethyl cyclohex 2 enol. Okay, so 1 is implicit for the alcohol. Don't forget that you can have cis or trans and R and S, so your stereochemistry. S, 2-hexanol. So first priority, second, third, fourth is the hydrogen going away from you. Okay. Put your left hand with its thumb going towards the screen. So first priority, alcohol. 1, 2, 3. Follow it with your left hand. For alkenes, remember EZ. Okay. So again, priority will now be your alcohol. So 1, 2, 3, 4, 5. Okay, this is an okay. So it's a pent 10 to all or pent 3N to all. Okay. First easy, remember again. High, low. This one carbon hydrogens, carbon and oxygen. So high, low. Okay. The high is here and the high is here. They're opposite sides. Okay, so E. Okay, remember cis trans. This can also be RS. Okay. And then the same thing here. So if you have more than two alcohols, it becomes a diol. So it becomes a, it's not a butanediol, it's a butanediol. Okay. So just remember that. Okay. Now, there are many ways to prepare alcohols, and most of these you've actually seen. So a lot of them, especially with the alkenes, you've already seen. But there are also going to be new ways that you can prepare alcohols, and I'll be focusing my attention on that more. Okay. So from alkenes, you've prepared alcohols the Markovnikov way using acid and water, or in a better example, okay, you've used oxymercuration. Okay. So the side with more substituents gets the OH, and the side with more the more hydrogens will get the hydrogen or the new hydrogen. Okay, so it's a Markovnikov addition. For the non-Markovnikov or the anti-Markovnikov, you have your hydroboration hydration. Okay, the side with more carbons gets the hydrogen. The side with more hydrogens gets the OH. We've also formed epoxides with alkenes using MCPBA, and then we treated either with acid or with base to create a diol. And remember the stereochemistry of this reaction. It's an anti-addition because the epoxide sort of resembles again that cyclic bromonium ion or halonium ion that you've seen before, right? The triangular intermediate. So base does an SN2 reaction, okay, backside attack to this carbon, releasing the leaving group. So it's an internal SN2 reaction. Okay, and then this one is just acid base to protonate to form an anti diol. For an acid base reaction, for the acid catalyzed reaction, it's a little bit more complex. Okay, so the first step is protonating your leaving group. So your epoxide, water acts as the nucleophile, backside attack, release. Okay, water gets back a proton to form your transdiol. Okay, if we change our nucleophile, let's say instead of water it becomes an alcohol, then you form an ether group and an alcohol group. Now, all of those are just reviews from what you've taken up before. The new part on how we can prepare alcohols would be through what we call redox reactions. Now remember redox, okay? Reduction means gaining electrons. Oxidation means losing electrons. Okay? But in organic chemistry, not only do we think about gaining or losing electrons formally, but we think about gaining or losing electron density. And we've grouped different functional groups by the electron density of the carbons. So the carbon with the highest electron density would be methane. So that carbon has the most number of electrons, it is the most negative or it's the most reduced. And then the carbon with the least or the smallest electron density would be carbon dioxide, CO2, and that would be the most oxidized form of carbon. And in between, so you have alkenes, alcohols, halides, primary amines, okay? And then you'd have carbons with even less electrons. So you'd have your alkynes, your carbonyls, okay? Dihalides, enamines, and then even more oxidized would be your carboxylic acids and esters, trihalides, okay? Nitriles, and then again, the most oxidized would be carbon dioxide. So going to, let's say, from alkane to alkene, that process an oxidation process, so losing electrons. And then the opposite, so let's say from alkene to alkane, that would be reduction. So if we follow this arrow here. When speaking about oxidation and reduction, we also speak about steps. So a two-step oxidation would go from alkane to alkyne. Okay, let's say from an alkyne, a one-step reduction would mean going only to alkene. So that would be H2 over Lindlar. If I had H2 over platinum or palladium, my alkyne would go for to alkene and then alkane. So it would be a two-step reduction. So the same thing happens with alcohols. Okay? If I had a carbonyl, let's say an aldehyde or a ketone, I could go back here and reduce it, turn it to alcohols. If I had the carboxylic acid or an ester, I could reduce it 2 steps to get my alcohol. Okay? So there. Again, we can reduce carbonyls and carboxylic acids to form alcohols. So one would be a one-step reduction, the other one would be a two-step reduction. Now, how would we do that? Okay? So a reducing agent that we could use would be a hydride ion. So an H or a hydrogen that has a lone pair. So it's a negatively charged ion. It's a hydride. It's not a proton. It's not an H plus. Okay? So a hydride ion can be provided for or provided by the reagent sodium borohydride, NaBH4. Okay? How does it work? So we have a carbonyl here. So in this case, it's a ketone. Okay? Let's look at the polarity of a ketone. Why is a ketone reactive? Because this carbon is partially positive and the oxygen is partially negative. Okay, which means that negative things like a hydride ion or reducing chemical would be attracted to this carbon over here. So what it does is that it can actually attack here, two heads, two arrows moving, okay? And since this carbon cannot take 5 bonds, it will force its pi bond to become another lone pair on oxygen. And what do you end up with? You will end up with, so we already have two lone pairs here, that's not shown. Okay, so two lone pairs and then add another one, it becomes three lone pairs. And an oxygen with three lone pairs is negatively charged. Okay, so now we have a deprotonated alcohol or an alkoxide. Okay, so ethoxide, I don't know how many carbons there are. Okay, so what's the point of the acid? The acid simply provides us with an H plus, so I'll simplify it. Okay, I won't use H2O plus. This will get that proton and it will become your new alcohol group. Okay, so again, carbonyls are reactive because they have a positive carbon. A hydride provided by sodium borohydride can attack that partial positive carbon, forcing this double bond to go to oxygen and become another lone pair. So from having two lone pairs, it now has three lone pairs. You have a new bonded hydride, and now your negatively charged alkoxide, very basic, or can grab an acidic proton, let's say from the acid that we add, and then it will now turn from an alkoxide into an alcohol. So this is cyclopentanone, a ketone, sodium borohydride, acid, cyclopentanol. I have an aldehyde or aldehyde here. So instead of having one hydrogen, it now has two hydrogens. It becomes a primary alcohol. Okay? Becomes benzylic alcohol. Now, this is something I need you guys to consider, but not so much anymore. Carbonyl carbons are sp2 hybridized, which again means they're trigonal planar. And if they're trigonal planar, then that means you can attack them from both sides, the same with the carbocation. So my hydride can actually attack from the top or from the bottom. Okay? So hydride attacks the positive carbon, pi bond becomes lone pair. Hydrogen hydride attacks the positive carbon, this time from below, pi bond goes to oxygen. And then again, you will end up with a mixture of different products. So this alkoxides or rather, will easily just get a proton, let's say from acid or from water, and then form your alcohol. Now, aside from sodium borohydride, okay, there's actually a stronger reducing agent. And by stronger reducing agent, I mean it's capable of doing a two-step reduction. And that's lithium aluminum hydride. So from sodium borohydride, lithium aluminum hydride, and then acid. The mechanism is absolutely the same, but unlike sodium borohydride, which can only reduce ketones and aldehydes, lithium aluminum hydride, more especially, can reduce carboxylic acids and esters to primary alcohols. Okay? Now, I'll show you guys the mechanism for that some other time or later, maybe. So, look at this example. This is an ester group, C-double bond O, O-R. It's a methyl ester, in fact. Sodium borohydride isn't a strong reducing agent, so it's only a one-step reducing agent. So it will actually cannot reduce an ester, so no reaction. Okay? But lithium aluminum hydride and an ester, this entire thing gets chopped off. This positive carbon will get two hydrogens here. Okay? And this O becomes an OH. And we lose that pi bond there. So it becomes this. It becomes a primary alcohol with two hydrides that we added. Okay? And this thing disappears. It turns into methanol, one carbon alcohol. Okay? So again, sodium borohydride can only reduce aldehydes and ketones, but it cannot reduce carboxylic acids and esters. Lithium aluminum hydride, however, can reduce both. So it's more selective, and then lithium aluminum hydride is more powerful. So if I have a molecule like this that has both a ketone and a carboxylic acid, with sodium borohydride, only the ketone gets reduced, but the carboxylic acid remains absolutely the same. With lithium aluminum hydride, the stronger one, ketone reduced, carboxylic acid also reduced. So, sodium borohydride, one step, and then your lithium aluminum hydride can do 2 steps. So, kaya niya both. Okay? Now, there's another kind of reducing agent that we can use. Okay? Instead of having a negative hydrogen, we can have a negative carbon. So, like a carbon ion. Okay. And that is what we know as a Grignard reagent. Okay. So, what are Grignard reagents? Grignard reagents are actually basically an alkyl halide, and then you have magnesium inserting itself between the bond of carbon and that halide, and that magnesium 2 plus forces the carbon to be a negative 1 and the halide to be negative 1. So it's what we call an organometallic reagent. So you have organic molecule and a metal. Okay? So you have an alkyl halide, let's say something chloride, something bromide, and then you add magnesium under a protic or non-acidic and aprotic environment, and then let's say you have an ether solvent, which is not protic, and then you get your Grignard reagent. Okay? Now, why do we have to use an aprotic solvent? Because Grignard reagents are exceptionally strong bases. So again, it's as if this carbon here is a carbon ion. So it has a lone pair and it's negative. This magnesium is 2 plus. It's positive 2. And this bromine is also negative. So negative 1, negative 2 plus positive 2 is 0. This carbon ion is very basic. So you can grab any of these acidic protons. Now, again, remember carbonyls are reactive to negatively charged nucleophiles because they have that positive carbon because of the polarity of the oxygen. So how did it happen again? So with the hydrides, but now instead of a hydride, you already have a negatively charged carbon from your Grignard reagent that will attack the positive carbon, forcing out this to be another lone pair. So again, there are 2 lone pairs here, and then now you will form a third set of lone pairs, and you get an alkoxide. You have a proton, let's say from an acid that you have later on when cleaning up your product. So let's put 3 lone pairs here. That 1 lone pair will grab a proton, let's say from acid, and then you finish up your product, which is an alcohol. So again, exactly the same mechanism with the hydride. Instead of being a hydrogen, now it's a negatively charged carbon. So that's what Grignard reagents are used for. Okay. So again, recall the redox levels and steps. Okay. Oops, sorry. As an example, I have a ketone, positively charged carbon and carbon. I have a Grignard reagent. In this case, it's a 2 carbon Grignard reagent with this carbon being your carbon ion, positive to magnesium, negative bromide, negative carbon. Okay, this one attacks here. Pi bond goes there. The alcohol, sorry, will be formed after the alkoxide grabs a proton from the acid. Okay, and then now we formed a new carbon-carbon bond. So in our case, our Grignard reagent had 2 carbons. So now it's going to be 2 more carbons added to what was once my carbonyl carbon. So ketones formed a tertiary alcohol. Now, carboxylic acids cannot actually react with Grignard reagents. Note again, Grignard reagents are very basic. So if you have an acidic proton, the carbon ion, instead of attacking this positive carbon, it will simply grab a proton. So carbon ion plus proton equals alkane. Okay, boring. And you just simply deprotonated my carboxylic acid. Simple as that. Okay. So again, remember, we need to make sure that our reagents and our solvents are aprotic or they don't contain acidic hydrogens because the Grignard reagent will simply get that hydrogen and it will not form a new carbon-carbon bond. Okay? So, Grignard reagents react with formaldehyde to form primary alcohols. So, I have here an alkyl halide treated with magnesium over an aprotic solvent like ether and heat. This becomes a negatively charged carbon, Mg2 plus Br minus. Okay? Negatively charged carbon attacks the positive carbon of formaldehyde, which is just a one carbon aldehyde. Bond goes there. And now we have an alkoxide. So formaldehyde is one carbon. So now we extended our chain by one carbon. And then what happens? Alkoxide treated with acid becomes an alcohol. So that's how you form primary alcohols with Grignard reagents. You have to use formaldehyde. If you use aldehydes that have one carbon group instead of two hydrogens, so a normal aldehyde, then you'd form a secondary alcohol. Another example of a Grignard reagent, okay? What if I had bromobenzene, okay? If I treat this with magnesium over ether, I can actually get this Grignard reagent. So it's a carbon ion that's actually part of a benzene ring. Okay? So this carbon ion can attack here, and this will go there, and then later on, a lone pair will get this proton, and now you formed a new bond to a benzene ring. Okay? But this was not Friedel-Crafts alkylation. Okay? This was a nucleophilic addition. So now you have a secondary alcohol. Okay. For a ketone, treated with a Grignard reagent, you form a tertiary alcohol. So again, attacks positive carbon, goes to the oxygen. Okay, this is an alkoxide. Okay, so negatively O, and then a positively charged MgBr, counter ion lang, gets an acidic proton, forms your tertiary alcohol. So you've seen this before. Now, esters, unlike carboxylic acids, do not contain an acidic proton, which means they're also reactive to Grignard reagents. But I said before that they react in a different or in a special way. Now, esters need to have a two-step reduction, which means that the reducing agent or your Grignard reagent has to add twice. How will it do that? Okay? So it's actually a more complicated reaction. And you will learn more about this later on in the semester or as the semester ends when we take up carboxylic acids. But it's important that you already know the mechanism now. Okay? So you have your positively charged carbon that contains a double bond O. So Grignard attacks here, going pi bond goes there, and you form your alkoxide. But your alkoxide actually does not become an alcohol. It will reform into a carbonyl. And how will it do that? It will reform its pi bond, but now instead of spitting out the Grignard reagent again, it will let go of your OR group in the ester. So this is now our leaving group. and it will leave as an alkoxide, or this will leave as a methoxide. Minus O dot 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 dot, it will leave as OCH3 minus. So this entire group will leave, leaving you with this, which is now a ketone. And then you know already the mechanism for how the Grignard will act with the ketone. So I have CH3 MgBr, so the carbon ion attacks this carbon, and this will go up here, and then this will become an alkoxide, grab an acidic proton, and then it forms your alcohol. Note, for an ester, the Grignard reagent adds twice. So since it adds twice, it forms a tertiary alcohol. So again, note the important steps. Nucleophile or Grignard attacks once, goes up here, but instead of this getting a proton to become an alcohol, it goes back to becoming a carbonyl. So pi electrons go back down and form a pi electron, sorry. And then we push out a leaving group. And then now that we have a ketone or an aldehyde, sorry, ketone for this case, now your Grignard can add the normal way and then form your alcohol. Note that this exact same mechanism can work for your hydride. So with lithium aluminum hydride, the mechanism is absolutely the same. The hydride from lithium aluminum hydride, which can reduce carboxylic acids and esters, will attack the positive carbon. Pi electrons go to oxygen, but that electrons and oxygens goes back down, reforms the pi bond, pushes out the leaving group. So for an ester, it's an OR group. For an carboxylic acid, it's just an hydroxide or a water group. And then you reform a ketone or an aldehyde depending on whether or not it's a Grignard reagent or a hydride that attacks. And then your hydride or your Grignard will attack the new formed ketone or aldehyde once more to form your alcohol. So a hydride would also add twice to an ester or carboxylic acid. Okay? Now, so those are the ways you can create alcohols. Now, what do alcohols do? Alcohols are one of the most important functional groups in chemistry and organic chemistry because they are very, very versatile. So from alcohols, you can do or produce so many other kinds of functional groups. Okay? So, you've already seen how we can prepare alkyl halides from alcohols. So let's say a tertiary alcohol, we can react with HX via an SN1 mechanism to form a new alkyl halide. So again, SN1 means we form a carbocation. So why is it so good that it's acidic? Alcohol group gets protonated. So a protonated alcohol group is a very, very good leaving group because the leaving group is water. So leaving group spontaneously leaves, you form a carbocation. You have a carbocation, nucleophiles like your halides can easily attack and form your alkyl halide. Now, what if I had a primary or secondary alcohol? Note from our lectures on alkyl halides that for primary and secondary alcohols, we have special reagents. Okay, you don't really need to know these mechanisms other than their SN2 reactions. So SOCl2 will turn your alcohol into a chloride. So dahil SN2 yan, you have to remember about inversion. So alcohol pointing right, now your chloride pointing left. PBr3 instead of a chlorine will introduce a bromide. So again, Inversion, alcohol facing right, bromide facing left. Okay. Okay, so that's our alkyl halides. What about alkenes? So alkenes from alcohols means elimination reaction. So tertiary alcohols or secondary alcohols, when treated with a very strong acid like H2SO4 and heat, okay, and even actually primary alcohols can undergo an E1 process. These are very, very extreme. So it has to be very, very hot, and you have to use a very, very strong acid like H2SO4. So again, acid protonates your alcohol. Protonated alcohol, very good leaving group, spontaneously leaves, becomes a carbocation, and then a base abstracts a proton adjacent to the carbocation for an E1 reaction to form. And note again, for E1, we like to form your Zaitsev product, which means you form the alkene that has more substituents on it. Okay, for secondary and tertiary alcohols, we can also induce an E2 reaction by using POCl3 and a base like pyridine. Okay, so E2 reactions, most important thing you need to know is that you can or you should be able to first form or grab a proton that is anti-periplanar to your leaving group. Okay, so alcohol group reacts with your POCl3 to form a dichlorophosphate intermediate, which is a good leaving group. Base abstracts a proton anti-periplanar to your leaving group to form your alkene. Oops, I'm low on battery. Okay, just remember POCl3 for secondary and tertiary alcohols, that's E2. You don't need to memorize this mechanism. Okay? Now, we've prepared alcohols using redox, remember, reducing either carbonyls or carboxylic acids or esters. Either one-step reduction or two-step reductions using hydrides and using Grignard reagents. Then that means we can also oxidize your alcohols back to those functional groups. And instead of using a reducing agent, now we need to use oxidizing agents. So if I have an alcohol, let's say a primary alcohol, I can do a one-step oxidation and turn into an aldehyde. I can actually oxidize one more step to carboxylic acids. If I have a secondary alcohol, I can actually only oxidize them one step into ketones. And if I have a tertiary alcohols, I cannot actually oxidize them anymore. What do you notice as the pattern? The number of steps of oxidation you have depends on the number of hydrogens attached to the carbon with oxygen. So if my carbon has two hydrogens, I can do up to two oxidations on it. If it has only one hydrogen with a secondary alcohol, I can only do one oxidation step. If it has no hydrogens, like with a tertiary alcohol, then I cannot actually oxidize it anymore. Okay, so here, primaries can be one step or two step, secondary straight to ketone, tertiary no reaction. Okay, for a primary alcohol, we can use a weak oxidizing agent or a one-step oxidizing agent to turn it into an aldehyde. And an example of a one-step oxidizing agent is periodinane. So it has an iodine that's in a positive 5 oxidation state. So it's a very positive iodine. It will grab electrons, and grabbing electrons from a carbon, it's oxidizing that carbon. So an alcohol, let's say in geraniol, with periodinane, gets turned into a geranial. Al meaning aldehyde. Now, what if I want to turn my primary alcohol into a carboxylic acid? So, two steps. I can use a strong two-step oxidizing agent like chromic acid, okay, CrO3 and H3O plus, or basically put CrO42 minus, a chromate ion, or even dichromate, so Cr2O72 minus. Okay, so trick is if you see chromium, that's a in a positive 6 oxidation state, then it's a very strong oxidation state or oxidizing agent. So this is the same reaction that happens during your chromic acid test in quali. Okay, so a primary alcohol, decan 1-ol, so 10 carbon alcohol, gets oxidized into decanoic acid. So very high yield, it's a very strong reagent with a chromium-based oxidizing agent, so CrO3 and acid, so chromic acid. Now, secondary alcohol stays at ketones. Okay, so secondary alcohol, if I use a strong oxidizing agent, let's say again, dichromate, so chromium meaning very strong two-step oxidizing agent, or even if I used a weaker oxidizing agent like periodinane, your secondary alcohol will always just go straight into ketone because it can only have a one-step oxidation. So, what alcohols would give the following products on oxidation? So I have a ketone here, just turn this into an OH group. I have an aldehyde, turn the aldehyde into an OH, and turn the ketone into an OH. Now for the aldehyde, if this were an alcohol form already, what kind of oxidizing reagent would we use to form an aldehyde? A one-step or a two-step oxidizing agent? So will it be periodinane or will it be chromic acid? The answer is periodinane. So both of these ketones, it doesn't matter if it's chromic acid based or periodinane, they will just undergo one-step oxidation. For this alcohol, since it's a primary alcohol, and you want to turn it into aldehyde, then we have to use a weaker oxidizing agent like periodinane. Now, alcohols help us form ethers. And an easy way to form ethers is via the Williamson ether synthesis, which is just an SN2 reaction between an alkyl halide and an alkoxide. So, I have an alcohol, sodium hydride, which is a strong base. The hydride will grab this hydrogen here and form a hydrogen gas, giving you a deprotonated alcohol or an alkoxide. Alkoxide, I have methyl iodide, or iodomethane. Since it is a methane group, very, very favorable ang SN2. And besides, no other reaction can occur with a methane. So, alkoxide, backside attack to this carbon, iodine leaves as a leaving group, and you now form via SN2 a ROR or an ether. So, cyclopentyl methyl ether. Now, again, remember, because this is SN2, you have to consider your steric hindrance. What if you want to create tert-butyl methyl ether? There are two possible ways of doing that. One is by using tert-butoxide to react with iodomethane. Another way is to use methoxide to treat with tert-butyl or iodide. Okay? If I used methoxide and tert-butyl iodide, also known as 2-chloro-2-methylpropane, then this carbon here is tertiary, where my leaving group is. Because it's tertiary, backside attack or an SN2 reaction is not favored, which means the ether won't form. And aside from that, it's tertiary, you have a strong base, your methoxide or alkoxide, a very strong base. Tertiary plus strong base equals E2, So if you look at this mechanism, this is an E2 reaction and it forms an alkene rather than forming your ether. So E2 versus SN2. So when designing your ether, you have to take a look at the different possible synthetic routes that you will use, considering that it's an SN2 reaction, which is sensitive again to steric hindrance. So I want you to try this problem on your own. Which of these two possible combinations of alkoxides and iodides would give the better mechanism to form your ether, your cyclohexyl methyl ether? So pause this video and try to think it through. Okay, so the first choice, secondary iodide plus methoxide, secondary plus strong base equals E2 reaction. So this will be the major product. The ether will just be the minor product. But if I used cyclohexanol as my alkoxide, so cyclohexanoxide or cyclohexanoate or nolate, okay, I treated with methyl iodide or iodomethane. Again, methylic means no other reaction other than SN2 can happen as long as it's a good leaving group, and iodine is a good leaving group, so SN2 will happen, and this will be the 100% product. Now, phenols are alcohol groups that are attached to a benzene ring. Okay, phenols cannot be dehydrated with acid, so I can't treat it with H2SO4 and heat, and it will form a triple bond here. So nope, that won't happen. I cannot use HX to turn it into an halide. So nope. But phenols can undergo Williamson ether in synthesis. So we can form ethers with them. So we can use a base to turn my phenol into phenolate. Okay. And then that phenolate can attach or attack via SN2 your halide or something. So in this case, a primary halide, which is, since it's primary, SN2 is still favorable. So negatively charged oxygen, after being deprotonated, attacks this, backside attack, and then bromide is lost, and you formed a new ether group. And also, since phenols contain aromatic rings, then of course they can also react via electrophilic aromatic substitution, which you have to review. Okay. Now, biologically, phenols are very important because when you oxidize phenols, so phenol, they form quinones. So quinones. So quinones look like this. It's like a double ketone on a ring. Okay. So oxidizing agent like sodium dichromate, phenol, quinone. Okay. Quinones can transform into hydroquinones. So it's like a double phenol now by the aid of electron transfer. So if we reduce it, let's say with tin chloride, it forms your hydroquinone, so double phenol. At the same time, my hydroquinone, if I oxidize it, let's say with sodium dichromate, it goes back to your benzoquinone, your quinone. So benzoquinone and then hydroquinone. Now, you don't need super to memorize this, but it's very important, especially for a lot of you who will be going into biochemistry and into molecular structures and mechanisms in your cells, in your body, metabolism. So this reaction happens a lot. Okay? So in our body, let's say when we have to metabolize certain things, let's say there are a lot of redox processes that happen. And when redox processes happen, we have to change or move around electrons, so change oxidation states. Coenzymes are the different chemicals that move around our bodies or in our cells rather, carrying these electrons or taking these electrons. And a lot of their coenzymes contain, or some of them contain, your kinones or your hydroquinone forms. Okay? So this is coenzyme Q10, which is very important in your electron transfer chain or electron chain transfer. Okay? Basically how you produce energy from breathing oxygen, okay, and how it creates carbon dioxide and stuff like that, okay. So you have your oxidized form, so it is like an electron sink. It can easily accept electrons, and once it accepts two electrons, it turns into your hydroquinone form, okay. Your hydroquinone forms, again, phenol with two OHs. That hydroquinone form can easily give up its electrons and give it to some other chemical in your cell, and it reforms back here. So it's like a cycle, and it can easily change form and carry electrons around. That's why these are very useful substances in your body. Okay. Ethers are very, very unreactive substances. One of the only one of the only reactions that ethers undergo would be acidic cleavages. Okay? So you have an ether, you treat it with acid, and it splits apart, and it turns into an alcohol plus some other chemical, let's say like an alkyl halide. So it's basically the reverse reaction that happened before. Now, depending on the nature of your ether, it would either be an SN1 or an SN2 reaction. Okay. The first step, however, for both would be the protonation of your ether. So, ether takes the acidic hydrogen, electrons go here, you form an protonated ether. Now, here's the trick. You have to classify the carbons of your protonated ether. So in our case, I have a secondary carbon here and a primary carbon here. Neither secondary nor primary would be suited for an SN1 reaction. So none of them would form spontaneously a carbocation. But the primary carbon is very prone to SN2 reactions. So the iodide that we form from our acid can easily attack the primary carbon, backside attack, release its bond to the OH or the protonated ether group. Okay. And so you form your primary halide and then your secondary alcohol. Now, what if I had for my ether a tertiary carbon and a primary carbon? Okay. Then once your ether group is protonated, okay, the protonated group or this entire thing can easily leave on its own as a primary alcohol. And when it does, you can form a very stable tertiary carbocation. And that tertiary carbocation will then have the bromide attack that and form your alkyl halide. So if you have a tertiary carbon attached in your ether, during acidic cleavage, it will undergo an SN1 reaction. Now, just some quick knowledge that you won't really need for your long test, but again, very important for biochemistry. Ethers and alcohols have sulfur analogs because oxygen and sulfur are in the same group, so they have similar chemistry. So the alcohol version of sulfur are called thiols. So let's say ethanol becomes ethane thiol, cyclohexanol, cyclohexane thiol. Okay, the thiol group, instead of being called a phenol, it's called the mercapto group. So benzoic acids or mercaptobenzoic acid. Ethers are called sulfides. So the sulfur version of ethers are sulfides. Dimethyl ether becomes dimethyl sulfide. Methyl phenyl ether becomes methyl phenyl sulfide. So on and so forth. Never mind that. It's a bit complicated na. Okay. So thiols can form similarly via your Williamson mechanism, and so can sulfides. So I have here SH minus, or your thiolate an ion, hydrogen sulfide ion. So hydrogen sulfide, backside attack primary halide, halide goes away, and now we have your new thiol. Or what if I had thiolate? Thiolate can backside attack, let's say, a methyl iodide or iodomethane, forms a new bond, tadan, now you have a sulfide. Unlike alkoxides, sulfides, okay, hydrogen sulfide or alkyl sulfides, are very nucleophilic. Again, because sulfur is bigger than oxygen, the negative charge is more spread out, and so it's more stable. And a more stable negative charge means more nucleophilic than basic. That's why substitution reactions are a lot more favorable. Okay? So just like with phenols, thiols and sulfides are very important biologically because of their redox properties. So thiols, when you oxidize them, and you can actually combine them and form a disulfide, so it's like a peroxide, RSSR. Okay? So your hair contains a lot of proteins, and proteins contain a lot of thiol and disulfide functional groups. Now, disulfide bridges in proteins gives them your shape, and the shape of your proteins gives the shape of your hair. Okay? Now, imagine if in your hair you have linkages that are weird. Okay? Weird linkages mean that your hair becomes frizzy. Okay? So these are all disulfide bridges. What hair rebonding does is that it actually breaks all of these disulfides. And to do that, since this is an oxidation reaction, we will use a reduction reaction. And you break them all up. So there, no more bridges in between. So your proteins are now flat. Once your proteins realign and they have their free thiols here, SH, 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 you can then add, let's say, a peroxide, which is an oxidizing agent, to reform new disulfides and new bonds. So when you formed a new bond, you rebonded. That's why your hair is rebonded, becomes straightened, because now your proteins realigned, straightened up before forming the new disulfide bonds. Ta-da! Okay? And then again, in your cells, okay, they handle stress or oxidative stress using disulfides, okay, or so thiols forming disulfides, or disulfides forming thiols. So if I have thiols, let's say in the different proteins in my body or in different chemicals like glutathione, okay, it undergoes, let's say, oxidative stress. That oxidative stress is taken by your body and then turned into or taken as an oxidation process, and that oxidation process forms a disulfide. And then disulfide, let's say there's reductive stress, can be broken down into glutathione. Okay? So as an oxidant, it prevents your cells from experiencing oxidative stress or oxidative degradation. Okay, so there. Now, the phenol part and the sulfides and the disulfides, they're really on a need to know or a good to know basis. But the bread and butter for this course would be your alcohols. So let's try to review how much you've learned about alcohols and what reactions they can do. So I want you to pause this video and think how you can transform phenylethanol into these following chemicals. So styrene, meaning there's a double bond here between these two carbons that used to have a single bond only. Phenylacetaldehyde, which has the alcohol turned into an aldehyde group. Phenylacetic acid, which has this alcohol turned into carboxylic acid. Benzoic acid, which is different because now instead of having two carbons here, there's just one carbon that's a carboxylic acid. And then last is ethylbenzene. So how does this alcohol disappear and simply turn into an alkane? So pause this video and figure that out. Okay, so primary alcohol into alkene. How do we do that? We can use a very, very forceful dehydration using H2SO4 in heat, which is E1 in a strange way. But since that's not very favorable, we can simply use a strong bulky base like tert butoxide to force an E2 reaction to happen. Next, primary alcohol to aldehyde. Do we use a strong oxidizing agent or do we use a weak oxidizing agent? Of course, the answer is a weaker oxidizing agent like periodinane. So if I used a strong oxidizing agent like the chromium-based ones, then you end up with an acetic acid group. Okay. The fourth one is a bit tricky because it's not so much the chemistry of alcohols as it is the chemistry of benzene rings. So note, benzene rings, if there's any alkyl group attached to it, and you oxidize it with KMnO4 for so long as there's one hydrogen in that benzylic position, then you will simply chop everything off and turn it into a benzoic acid group. So then, KMnO4. Last, we don't know any direct ways to turn an alcohol into an alkane, but we know how to dehydrate it into an alkene. So again, H2SO4 or bulky base, bulky strong base. And then from alkene, we can easily turn that into an alkane by reduction, H2 over Pb. Okay, here's another synthetic route, and I just want you to propose what reagents we used to form these products. So A, turn this cyclohexanone to cyclohexanol, cyclohexanol to cyclohexylbromide to one other carbon added, but it's an alcohol. This alcohol turns into an aldehyde. What reagent is that? From an aldehyde to this big molecule here. Oh no. And from this big molecule here with an alcohol, how does it turn into an alkene? So I want you to pause the video and start figuring it out. Okay. Oops. So let's try this out. So from ketone to alcohol, is that addition? Is that elimination? Is that reduction or oxidation? So it's reduction. So we can use a oxidizing agent like sodium borohydride, or in fact even a strong reducing agent like lithium aluminum hydride. Now, secondary alcohol to bromide, PbR3. If this were chloride, this would have been SOCl2. Okay? Now, from bromide to a one extra carbon added alcohol. So this is actually two steps. This is one to convert it into a Grignard, so by adding Mg over ether. And then since you have to add one more carbon, then we use formaldehyde. So the formaldehyde, so Grignard attacks the formaldehyde. This goes there, becomes an alkoxide, then acid will simply turn it to an alcohol. Next, from an alcohol to an aldehyde. Strong oxidizing agent, weak oxidizing agent, or reducing agent. So that's a weak oxidizing agent. So one-step oxidizing agent. So periodinane. Next, from this cyclohexane with a methyl cyclohexane group, okay, to a big molecule. Obviously, since we have an aldehyde here, we have to use a Grignard reagent. And how big should that Grignard reagent be? So we have cyclohexane ring and one carbon. Cyclohexane ring and one carbon. So the Grignard reagent will be this carbon here and the benzene ring. So pH, benzene, CH2, MgBr. So chop it here. And then again, it will form an alkoxide. Alkoxide needs to be protonated with acid. Last, from this alcohol to an alkene, simply use concentrated acid or a strong base. And then voila. Last, I want you to try to propose your own synthetic route of how you can turn cyclohexanone, which is just 6 carbons with a ketone group, how can you turn that into that? Okay, how? So I want you to think about that. Note that we have new carbons and we have an alkene here. So think about that, pause the video, and then press play once you've sort of tried to figure it out. So here, okay, it's a very similar synthetic route as before. To be able to form new bonds with carbonyls, you guys know how to use Grignard reagents. And where do Grignard reagents come from? They come from alkyl halides. Now, can we go from a ketone to alkyl halides directly? Nope, but you know how to go from ketone to alcohol by a reducing agent, and then from alcohol to a bromide or a halide via a halide, or sorry, a substituting agent like PBr3 or SOCl2. For bromide, PBr3. Then from alkyl halide, you can form your Grignard simply by putting magnesium over ether. Okay? Then once you have this alkyl halide, you can react it with another molecule of cyclohexanone. It will form this. Right? 6 carbons in a ring attacking a 6 carbon in a ring carbonyl. So the carbonyl oxygen becomes an OH because of the acid. And then now this OH can easily be dehydrated with strong base or H2SO4 in heat and turn into an alkene. So that's it. I hope you guys enjoyed this lecture. See you in class.